let's talk about an idea in math that is so simple, so intuitive, it just has to be true. But if you accept it, you suddenly find yourself in a world where some lines have no length at all, and you can take a solid metal ball, add nothing to it, and somehow turn it into two identical copies of itself. Yeah, it feels right, it works, but it also leads to some of the most mind-bending paradoxes imaginable. So really, how is that even possible? How can one simple statement just tear a hole in our basic understanding of reality? Well, it all kicks off with something that sounds incredibly easy: the act of making a choice. All right, let's get right into it. The whole issue, the seed of all this weirdness, starts with a question that's way harder than it looks. How do you actually choose something in pure mathematics? I mean, sure, you could just think of a number, right? Say 27. But in math, that's not a real process. That's just your brain doing something. It's not a repeatable, logical rule. For a simple set, like all the positive whole numbers, the rule is easy. Pick the smallest, and boom, you get one. But what happens when the numbers get messy? Let's try it with the real numbers. Now remember, that's everything. All the whole numbers, all the fractions, and all the weird irrational numbers like pi. So, if I ask you to pick the very next real number right after 1, what do you pick?
You might say, okay, 1.1, but then I can just say, nope, 1.01 is closer. And you'll come back with fine 1.01, and I'll say, what about 1.001? We can play this game forever. There is no single definable next real number. You can't point to it.
And that's the heart of the problem. We've got this infinite spray of numbers between 1 and 2, but without a clear, defined rule to select the very first one, we're totally stuck, mathematically speaking. And this exact problem absolutely captivated a mathematician who was about to change how we think about infinity itself. And that man was George Cantor. He was a brilliant German mathematician. And at the time, everyone just assumed that infinity was, well, infinity, that all infinite things were the same size. Cantor was about to detonate that idea completely. What Cantor showed was that infinity comes in different flavors, different sizes. There are countable infinities, which are sets where you can actually line up every single element, one-to-one with the counting numbers. But then he proved that other infinities, like the set of all real numbers, are just bigger. They're so vast, you could never, ever list them all. They are uncountable. And the way he proved it is just beautiful. This is his genius move. He basically says, okay, let's pretend you're right. Imagine you could make a perfect, infinite list of all the real numbers. Then he shows you exactly how to build a brand new number that by its very construction cannot possibly be on your list. It's this brilliant, airtight contradiction. He proved that no matter how infinitely long your list is, it's never actually complete. The infinity of real numbers is just a bigger kind of infinity. This discovery was a bombshell in the world of mathematics. But for Cantor, it was just step one. His real obsession, his ultimate goal, was to prove that even these huge, uncountable infinities could be put into some kind of definite, ordered line. And that pursuit, it would end up costing him everything. The key idea he was chasing is called a well-ordered set. And it's pretty simple, really. It's just a set where, no matter which piece of it you grab, that piece always has a definite first element. You always know where to start. The natural numbers are like this. Even the integers, which go to negative infinity, can be wrangled into a well-ordered list if you rearrange them, like 0, then 1, then -1, and so on. Cantor was convinced he could do this for any set, even the uncountable real number. But he couldn't find the proof, and his ideas were met with absolute, vicious hostility. His own former professor, Leopold Kronecker, led the attack, publicly calling Cantor a charlatan and a corrupter of youth. He did everything he could to destroy Cantor's career. And for Cantor, who was a deeply religious man who thought his insights were messages from God, these attacks were personal and devastating. The pressure was just crushing. After years of relentless attacks, and one particularly awful public humiliation where his great theorem was dismissed as just plain wrong, Cantor couldn't find the proof he so desperately needed. He suffered a series of severe nervous breakdowns, and in the end, he abandoned mathematics completely, a truly broken man. But here's the thing. Cantor's idea wasn't wrong. It was just incomplete. It needed a hero. And that hero turned out to be Ernst Zermelo, another mathematician who had a sudden realization. Cantor, and basically all other mathematicians, had been using a hidden assumption this whole time without even knowing it. Zermelo took this hidden assumption and gave it a name, the axiom of choice. Now here's the crucial part. The axiom doesn't give you a rule for how to choose. Imagine you have an infinite collection of shoeboxes, and each one has at least one pair of shoes in it. The axiom just says, yep, it's possible. It guarantees that you can create a new set by picking exactly one pair of shoes from each and every box, even if you don't have a specific instruction, like pick the red ones. It just asserts that the final collection of choices can exist. And with this axiom in hand, Zermelo could finally prove Cantor's theorem. He essentially said, look, with the axiom of choice, I can just pick a real number to be the first one. Then, from all the numbers that are left, I'll just pick a second one, then a third. The axiom guarantees this infinite chain of choices is valid. He then used some of Cantor's other wild ideas, called transfinite numbers, to make sure every single real number got a label and a spot in line. The result is a bizarre, scrambled-up list that looks nothing like our familiar number line. But it works. It's a well-ordered set. Cantor had been right all along. So, case closed, right? Zermelo saved the day, proved Cantor right, and gave mathematicians a fantastic new tool. Well, not quite. Because this tool, the axiom of choice, unlocked a Pandora's box of consequences that were bizarre, totally counterintuitive, and what most people would call paradoxical. One of the first strange things to pop out came from a guy named Giuseppe Vitali. Using the axiom, he managed to construct a set of points on a line that just broke the whole idea of measurement. Its length couldn't be 0 because you could stick copies of it together to fill a whole line segment, but its length also couldn't be any positive number because if it were, infinite copies of it would have an infinite length, which is impossible. It was a collection of points that had no definable size. And then came the big one, the most famous paradox of all. In 1924, two mathematicians, Banach and Tarski, proved that if you accept the axiom of choice, you can take a solid sphere, break it into just 5 special, infinitely complex pieces, and then, just by rotating and moving them around, reassemble those same pieces into 2 perfect, solid copies of the original sphere. No tricks. The reason it works is that those pieces are unmeasurable sets, like Vitali's. They don't have what we'd call a volume. And this was the crisis. The axiom of choice feels like common sense. Of course you can pick one item from each box. But the Banach-Tarski paradox feels like it violates the laws of physics. It feels impossible. So, what on earth were mathematicians supposed to believe? For decades, the entire math community was fiercely divided. And the way out of the mess wasn't about proving the axiom right or wrong. It was about fundamentally rethinking what an axiom even is. And nothing, I mean nothing, captures the total chaos better than this story. When Tarski, of the sphere paradox, submitted a paper showing the axiom was logically equivalent to another statement, one editor at a top journal rejected it flat out, saying basically, we're not interested in a paper proving that 2 false statements are the same. So Tarski just sent it to another editor at the very same journal. That editor also rejected it, but his reason was, we're not interested in a paper proving the equivalence of 2 statements that are obviously true. The final answer, which only came in the 1960s, was a huge shock. The axiom of choice can't be proved, and it can't be disproved from the other axioms of math. It's truly an independent choice. It's a lot like the famous parallel postulate in geometry. If you accept that one straight line can be drawn parallel to another through a point, you get the standard, flat geometry we all learned in school. If you reject it, you get a totally different but equally valid geometry, like the curved geometry on the surface of a sphere. Neither one is more correct. They're just different systems built on different rules. And the axiom of choice is the same. You can accept it and get a very powerful version of math that comes with duplicating spheres, Or you can reject it and get a less paradoxical but much clumsier mathematical universe. Today, most mathematicians do choose to accept the axiom. The proofs it allows are just too elegant and too powerful to give up, paradoxes and all. And what this whole story shows us is that mathematics isn't always this rigid, pre-existing world we just discover. Sometimes it's a world we actively choose to build, which leaves you with a really fascinating question. What other obvious truths that we all take for granted are actually just a choice that we haven't even realized we're making?